The wheatstone bridge is a powerful theoretical tool for finding an unknown resistance, but to bring it into the lab, we use the meter bridge. We take the bottom two resistors of the diamond and replace them with a single, uniform wire stretching exactly 100 centimeters from point A to point B. We place a known resistance, S, into one gap and our unknown, R, into the other. By sliding a galvanometer's jockey along the wire, we look for the balance point where the current stops flowing. This divides the wire into two measurable lengths, L on the left and 100 minus L on the right. To turn these physical lengths into electrical values, we define RCM as the resistance per unit length of the wire. This allows us to treat each segment of the wire as a specific resistor. Since the wire is uniform, that resistance per centimeter appears in both the top and bottom of our ratio. This means RCM cancels out entirely, leaving us with a relationship defined purely by the lengths we can see on the ruler. This gives us our final baseline formula. Because the precision of the measurement is tied to the ratio of these two lengths, you'll find that aiming for a balance point near the 50 centimeter mark provides the most reliable results and minimizes potential percentage errors in the lab. Solving a complex problem requires tracking how the bridge responds to change. In this scenario, we have three specific conditions. The resistors are interchanged, that swap causes a 10 centimeter shift to the left, and the total series resistance of the two components is 1,000 ohms. We begin by defining the initial state. In this first scenario, before any changes are made, we use the baseline formula to establish equation 1, which describes the original valence point at length L. For the second scenario, we physically swap the resistors. Now S occupies the left gap and R is on the right. This swap causes the balance point to move. Since the problem specifies a 10 centimeter shift to the left, our new left side length becomes L minus 10. To find the new right side length, we subtract that new value from the total 100 centimeters. 100 minus the quantity L minus 10 leaves us with a new right side length of 110 minus L. We now have equation 2. By translating these system of equations that describes how the same components behave in two different configurations. At this point, I recommend pausing the video. Try setting these two expressions for S equal to one another, canceling out the R, and expanding the terms yourself. When we set equation 1 equal to equation 2, the unknown variable R appears on both sides. This allows us to remove it from the calculation entirely for this step. To clear the fractions, we cross-multiply the remaining terms. Multiplying out the binomials results in the polynomial equation. While it looks complex, the solution is closer than it appears. Notice the L squared terms on both sides of the equal sign. Because they are identical, they cancel each other out, and our quadratic equation simplifies into a much easier linear one. After grouping the L terms and solving, we find that the original balance point L was exactly 55 centimeters. Now that we have the length, we can return to the ultimate goal, finding the value of the unknown resistance R. We still have one remaining piece of information from our initial parameters, the total series resistance. Since S and R together equal 1,000 ohms, we can express S as 1,000 minus R. By substituting our found length of 55 centimeters back into equation 1, we determine the exact ratio between our two resistors. We then plug this ratio into our series resistance equation. This gives us a single algebraic expression where R is the only unknown. Solving this final step shows us that the resistance in the left slot was 550 ohms. The path to solving any meter bridge problem is always the same. First, establish the standard state. Second, when the balance point shifts, carefully map the new lengths, finding the left side first, then subtracting it from 100 for the right. Finally, remember that methodical expansion is your friend. In these ratio-based problems, squared terms will almost always cancel out, turning even the most intimidating configuration into simple algebra.